Okay, good morning, everyone. Top Hat code for today is 0461. Top Hat 0461. Going to share my screen. And we'll get the chat ready in case anyone needs the chat. And we'll do the full-size slideshow. Okay, very good. So here we go. All right, so today we're going to talk about randomized algorithms, but in order to talk about randomized algorithms, we first need to talk about how we get random numbers. But before we talk about the random numbers, we're actually going to motivate this. All right, so what do we need random numbers for? Well, if you have a video game, right? So the video game isn't very interesting if the ball always goes in the same place, or the monsters that come out that you have to kill are always in the same place, right? It's not very interesting. So we need some randomization to handle that. Lotteries, right? This is a little bit of things turning around. So it used to be that you would, generate random numbers to do a lottery. Now there's also a question of how do we get random numbers, and sometimes we use physical phenomena for that, right? Encryption. Okay, so one way to do encryption is you take two very large random primes, right? Data collection, right? Let's say we need to get a sample of data. We want to determine if the concrete is good. So we need to draw samples of concrete from different places. Right? We can use random numbers to pick that. Or, of course, randomized algorithms that we're going to discuss today. So how do you get random numbers? Well, one thing you could do is you could ask humans, right? So I could do a survey. I could say, okay, everyone on the chat, write in a random number, write in a number between 1 and 100, right? And that would work pretty well, except when I do this in the classroom, I don't have a chat, I'll go to student 1 and say, give me a number. And I go to student 2. And you know what happens? Students are inclined not to give me the same number that someone else did. You know why? Because they say, well, someone else picked that. So that would look like a pattern, right? But in the reality is, if you have enough people, and there's something called the birthday paradox, you'll see that in a moment, then you actually would expect to get duplicates in a surprising way. So we'll talk more about that when we get to it, right? You could take the least significant digit of time. So you look at the system clock and you use let's say the last digit or digits. Why the least significant digit? Why the least significant digit, not the most significant digit? So around the most significant digit doesn't change very often, right? The century doesn't change very often. The millisecond, the microsecond is constantly changing, right? Similarly, last 4 digits of a phone number, right? Because that's the part that is likely to change. Whereas the area code in New York City, there are some main area codes and they're pretty constant. Or even the exchange, the next 3 digits within a neighborhood, I'm not talking about cell phones now, but within a neighborhood, those tend to change. In a cell phone, those next 3 digits are often, let's say you buy your phone at the Verizon store, you're going to get, they have a block of numbers with those 3 digits. So if you buy it from the same place, a lot of people are going to have those same middle digits there, right? Random.org has random numbers that they get from data in the atmosphere, all right? They're books. Believe it or not, they're actually books that list random numbers. You could also take digits in transcendental numbers like pi, e, the square root of 2, pull out numbers from there, which appear to have no particular sequence. And then there are these globally universal IDs and secure hash, right? So those are all random numbers. Right. Now, computers often don't have access to that kind of information. So what we do instead is we use a mathematical function called a linear congruential generator to generate these numbers, okay? Can anyone tell me what is linear about this? What makes this linear? So in CS 220, we probably learned about linear homogeneous equations. Learn about that versus nonlinear. Non-homogeneous. So what makes this linear is that it's a scalar multiple of a previous x, right? Not x squared, not x cubed, right? Just take x as it is, linear multiplier plus, if you like, a constant. So that's what makes it linear, all right? And we start with some kind of seed in x0, we multiply it, we increment, and we need a modulus. Okay, the modulus is important so that the numbers don't go crazy, right? They stay within a particular range, and this will generate random numbers. Okay, by the way, there are some review exercises. Some of them you're going to need to go online. So if you go to Wikipedia and you look at random number generators, linear congruential generators, there'll be some information there that will be helpful in answering some of the questions. All right. Okay, so these are called pseudo-random numbers. You know why they're called pseudo-random numbers? Because they're not really random. If you know the formula and you know the seed, then you know what all the numbers are going to be. So that's not so random anymore. The other thing that makes it not so random is random numbers, you expect to get duplicates here and there. And these pseudo-random numbers, once you get a duplicate, the series starts to repeat itself. So that's not really random. Random, you could get occasional repetitions, and it doesn't mean any series is repeating itself. So that said, they're useful because if I don't have access to a good source of random numbers, I need my computer to generate them. The other thing is sometimes this predictability is useful because if I want to test an algorithm, let's say I want to test a sorting algorithm, and I want to get the same random data each time for testing purposes, because I want to compare to what I did, and I want to know that it doesn't depend on the data, that it depends on the algorithm, the change in the algorithm. So being able to get the same list is actually useful. Right, so something that comes up in various cases is a random permutation. How do I get the data? And we have two choices, okay? One way is to look at this. We can call a Python function called shuffle. You call the, okay, so what you can do is you generate a deck, right? How do you generate a deck? You have a nested for loop. For I goes from 1 to 13, or you could iterate over a list. Okay, so I teach a course, Intro to Programming, and you could do something like this for rank in, you know what, maybe I'll do it here. So let's do something like this. Okay, give me a second here. Okay. Okay, so what you can do is you could do something like this for rank in, and you do something like this. You could say ace 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, and queen, and king. Okay, and then inside here, you could say for suit in, you could do club, diamond, and we could actually get the symbols for these, heart and spade. So you say deck equals an empty set, and actually, if you look at the old exams, I think I had a card game question. We're going to change this to Courier New. And we're going to get rid of the spacing. And let's make this a little smaller. Okay. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So you can say deck dot append, and then you can append the, you do it like this. Rank plus the suit. And then at the bottom, you could do this, deck. All right, so that will make this a little bigger here. Okay. All right, so here are some useful functions in Python. Okay, so some of this we've seen before in our class, some of that we haven't. Okay, so the first thing is, if you want to do random stuff, you import random. If you just call the random function, that'll give you a random decimal. If you want to get a random integer, notice that this is inclusive, unlike range, which is exclusive on the latter end. Right, so this will get you a random number between low and high. Another way to generate this, okay, is to take random times the size of the interval and then add low to shift it to the right place, and then take the int of that. Okay, so that's another way to do it using this function instead of that function, right? You can also get a random choice from a list that you specify. For example, let's say you want to create a random walk, and the random walk has 4 directions: north, east, south, and west. So you could make those 4 choices, and then you get a choice from that, right? You can get a random range, all right? So if I want to get a number in a particular range with a step, okay, step means, let's say I want odd numbers. So I start with an odd number and I use a step of 2. It's going to choose from 1, 3, 5, 7, and so on. All right, so I can use this for even and for odd. I can force the seed. This is useful if I want to get the same numbers as before. And I can also call the shuffle function. And this is very useful. So in the beginning of the semester, when we did first we did search, and then we did sorting, right? We spent some time coming up with a random list. This is a way to get Python to do the work for you. So basically you specify a range, how many numbers you want, and then it does the work for you. All right, so one of the methods that we had over here was something called shuffle, right? Where it will shuffle it for you. What happens if I don't have a shuffle method? I don't know that there's a shuffle method in Python. So you can use this function here that will basically swap numbers, okay? So you basically go to the particular number that you have, and then you swap them around, all right? So that's another way to generate a random shuffle. So what is the birthday paradox? Has anyone heard of the birthday paradox before?
Yeah, it's not exactly paradox, but it's likely that I think 20-ish people in the same room will share some.
Okay, so the rule of thumb is, well, yeah, it's not a pure paradox, but it's sort of an unusual phenomenon, right? Unexpected phenomena. So the rule is that if you have 23 people in a room, that already with 23 people, it's a 50% probability that 2 people will have the same birthday. So actually, in some semesters, I've actually done this experiment where I had a form, a Google form. I asked everyone to type in their month and day, and then, lo and behold, it, more often than not. Of course, now our class is roughly twice the size of that, so it's maybe not as surprising as you would have thought. But let's just run through the math for this, okay? Because the math, maybe it's not obvious to you. So What's the probability that someone will be born on January 20th? Or if you prefer, on August 8th? Okay, so the probability that no one will be born on January 20th means pick any other day of the year. So there are 364 other days of the year, and raise that to the nth power, right? Because that's a probability that no one will be on that particular day, right? The probability that someone will be born on that day is then 1 minus that, okay? So this is this is a pretty small number, which means it's a pretty high number that no one's going to be born. But here's the thing, right? Now we're looking at two people sharing the same birthday. So in order for no two people to share the same birthday, this is the math, right? This says that, okay, the first guy can be born on any day of the year. The second person can be born on any day but that day. The third person can be born on any day but those 2 days. The fourth person can be born on 362 of their 365 days, and so on and so forth. So the probability that two people are born on the same day is 1 minus the probability that no one is born on the same day, which is this. Now, it's hard to tell what that comes out to be, but it comes out, and you can do this in Excel spreadsheet or on a program, right? It comes out that with 23, when n is 23, this comes out to be about 0.5, which is pretty remarkable. Again, even though there are 365 days in the year, that the probability is about 50% that two people in a class of 23 have the same birthday. Now, what does this have to do with random algorithms? The answer is because when we think about random numbers, we're inclined to think there shouldn't be repeats, right? So if I ask the class for a number between 1 and 365, people are not going to want to repeat the same number that someone else gave if they know what other people gave. But in reality, we would expect to have in a class of 45, we would expect to actually have a lot of repeats, believe it or not. So that's one of the, that's where the paradox comes in, where it's sort of unexpected that you get repeats. Okay. So now we're going to venture into randomized algorithms. And when we talk about randomized algorithms, I don't know if we mentioned these terms before, maybe we did, that we have two basic categories, okay? We have Monte Carlo algorithms and we have Las Vegas algorithms, right? Let's start with the second one first. A Las Vegas algorithm means we will get the right answer using a randomization, but what won't be predictable is the time complexity, all right? So it means, we will, so for example, quicksort, right? Quicksort, we use a randomized pivot in one of the implementations. So it's guaranteed to be correct. Quicksort, if you code it correctly, is always correct, including with a randomized pivot. What's not guaranteed is the time complexity, right? It could be log of n log n, it could be n squared, it could be somewhere in the middle, right? Monte Carlo algorithm is the opposite. It says the time complexity is guaranteed, right? We could write a Monte Carlo algorithm that will always do it in n log n, but it might not give us the right answer. Well, what good is that? Well, the answer is we had this lecture on approximation algorithms on Thursday, where we said, you know what, approximation algorithms are sometimes useful because it'll be good enough. And not only will it be good enough, but it's so critical to get it in the right time frame. Okay. So these are some of the randomized algorithms that we've seen. Some of them are randomized data structures, some are algorithms. And if anyone can think of another example that that isn't listed here, let me know. I'll add it to the slide. Okay, so one of them is randomized binary search. I think that was our very first example this semester, right? Where instead of always using the midpoint, we find another pivot. Okay, that's why I put midpoint here in quotes, because it's not really a midpoint. And then we search on one side or the other. We had BOGO sort, where you use a randomized, and notice in parentheses, I'm telling you whether it's a Las Vegas or a Monte Carlo, all right? So BOGO sort, we take a random permutation of the data and we check if it's sorted. If it's sorted, great. If not, we try again. So it will always get the right answer eventually. It just might take years. It might take centuries. It might take millennia. So the BOGO sort could take a very, very long time. Then we had quick sort and quick select, where we use a random pivot to determine where, where the left part is and where the right part is. Okay, those are basically essentially the same idea, not all that different from the randomized binary search. We had the Raven closest point in computational geometry, right? So we, out of our n points, we took n square root of n points, and we found the closest pair of those, and then we broke the grid up into these little D by D boxes. And then we looked inside the boxes as well as the 8 neighbors to see if there was anything there, and we found the closest point of those, right? We had a TREEP, which was a data structure, a combination of a heap and a tree, a binary search tree, and we assigned a second number to each node. So the node has the key, but it also has a heap value, and we maintain a heap property of those values and a binary search tree of the keys. What that does is, this is one of many strategies to keep the binary search tree balanced, just like a heap is balanced. And we have skip lists, which is like a linked list, except instead of only being able to go one step ahead, from 1 to 2 to 3 to 4 and 5, or maybe if it's doubly linked, to go from 10 to 9 to 8 to 7, we can skip around. How do we determine where you can skip to? We use random numbers, and that enables us to jump around pretty freely, so we don't always have to go, one by one to get to a particular point. We add a Bloom filter, which is a kind of hashing function. And what does a Bloom filter do? The Bloom filter enables you to determine relatively quickly whether something is in the data structure or not, right? So if all the hash functions, let's say you have 10 hash functions, and they all give you a 1, they give you a yes, a true value, then we conclude with high probability that the item is there. If any one of them fails, then it's not there. We had Raven-Karp. Raven-Karp was one of our 4 string matching algorithms. It uses a hash function on the pattern, a hash function on the text, and if they match, it's good. But that could lead to false positives, right? They match, but they're really not the same thing. So we say, well, let's take 5 hash functions. And if all hash functions are the same, then we conclude with high probability that it really is the same. And then we had the Karger min cut, right? So we're trying to break up a graph into 2 parts. And Karger said, basically, you pick an edge at random, and then you take all the edges that were incident to that, and you collapse them. You called that a contracting graph. Can anyone think of any other examples from our course? Why is Bloom random? Okay, so Cheng is asking, why is a Bloom filter random? Because we have a bunch of hash functions, and the prime number in the hash function is usually chosen randomly. It doesn't have to be. Most of these things don't have to be random, but it's chosen randomly. And then, just 1 second, the recording from my previous class is saving. I just need to press OK, and I will be back with you guys. Okay. So generally, we use a bunch of hash functions, and we choose some of them at random, or we pick the modulo at random. So that's the idea there. Any examples that I'm missing?
Median of medians, I think, because you picked the 5.
The median of medians. So the median of medians per se is not random. It's chunks of 5.
Can you pick those randomly?
Those are no, they're not random. No, they're not random. They are, every 5th element. I'm sorry. It's you take the size of the array, you break it up into chunks of 5, and you find the median of each chunk. So that's not random. It could be in conjunction with quick select, but it's actually an alternative to the random pivot. It's saying use the pseudo median found by the median of medians, and then use that, and that will give you a pretty good approximation, which you can then use for the quick select. So I would say that's an alternative to random. Okay, so if you think of something great, and if that's all of them, that's also good. All right, so here's some more randomized algorithms. I'm not going to go through this list here because we're just going to go through them in context. So All right, so here's an example. Let's say you want to find the minimum number in a group. Okay, so we've talked about this in our lecture, numerical algorithms. How do you find the min? Well, you make the min the smallest, the first one, and then you go through it one by one. If anything is less than it, fine, that takes order of n minus 1 operations. If you want to find the min and the max, it takes 2 times that. If you want to do the min and the max together, we talked about that. You can get it down to approximately 3 times 2 over, 3 over 2 times n, right? 1.5 n approximately. So the question is, can we randomize this? And the answer is yes. What we do is we take a bunch of numbers, a subset, and we look at the min of that. And we use that as our min. So instead of taking all n numbers, we take k numbers. Now, if n is small, it's like 10 or even 100, just not worth it. Just get the real min. What happens if n is a billion or a trillion, right? So we don't necessarily want to go through a trillion numbers to find the min. So we take, 1,000 of them, and that'll give us, might give us a pretty good idea of what the min is, all right? So again, it's not guaranteed. So by the way, would this be a Monte Carlo or a Las Vegas?
Monte Carlo, since so
That's a Monte Carlo, right? Why is it a Monte Carlo? Because it doesn't give us the right answer. Probably will not give us the right answer. But its time complexity is bounded, right? It's O of k. All right, so that's a Monte Carlo, correct. All right, we want to find the median. So we spent a lot of time, maybe a good part of a lecture, talking about how to find the median, right? But because of randomized algorithm, we sort of did this a little bit, right? We took 3 elements and said, okay, the median of 3. But the median of 3 is not really a very good approximation. But what happens, again, if we have a billion elements, and we take 100 of them, 1,000 of them, and we find the median of that, that might be a decent approximation, right? So here's a recommendation. If we pick our k to be log of n, okay? K is the number of items that we're looking at. So if n is, I don't know, is a billion, and we take the log of that, it depends on the base, obviously. Let's say a log base 10, right? So we look at 9, so some multiple of 9, 90, 900, something like that. So we're going to get a, the time is going to be short. Okay, and we'll get an approximation. Okay, again, it's not guaranteed, but it depending on how big k is, we could get a good number. All right, binary search, we talked about this already. So usually I don't do randomized binary search at the beginning of the semester, but this time we did it as part of our little program there. So again, randomized algorithm and normal binary search, you find the midpoint between low and high, exactly halfway. Randomized says, you look at a randomized point, okay? The reason for this, why would you use randomized? Is it just more work? At the end of the day, it's actually worse time complexity, right? It's O of n, worst time. Average is still log n. So why would you use it? The answer is, if you got a lot of numbers that are clustered together, so half of your array are big numbers and you're going to be in that range, you might be better off the randomized algorithm that'll split that chunk a little faster. Okay, merge sort. So this one we didn't talk about, right? So in regular merge sort, what do? We split it halfway and we do the left and we do the right, right? We could apply a randomized approach to merge sort where we break it not in half, but some on the left and some on the right, right? What's the advantage to this? Again, if you get these clusters, okay, if it's distributed uniformly, you're better off in the middle, but it is an option. All right, binary search tree and a tree. So we talked about this in our lecture on data structures. So here's the same slide again, just to remind everyone. So notice in this picture, we have 2 things going on, okay? The green, the top number in each node is the key. That is the traditional key of a binary search tree. And you notice it has a binary search tree property, right? 30 is less than 50, 70 is greater than 50, right? 20 is less than 30, 40 is greater than 30. But there's a second number here. Second number here is a randomly assigned number. And you'll notice that we are preserving the heap property. Okay, so where we no longer have the heap property, right? So let's say we add an 80 and we get a 12 over here, but the 12 should be higher up. So we have to do a rotation of the data so that we preserve the heap property as well as the binary search tree property. So now 70 is to the left of 80, but the 12 is on top of the 10, right? So you're not responsible for the actual operations that do that, but that's the idea. We're using randomization in the context of a data structure, right? So among our data structures, we had a tree, we had a skip list, and we had a Bloom filter, right? Those are examples of randomization on the data structure side. All right, so here's something we haven't seen before, which is a primality testing. So we actually have seen primality testing. What we haven't seen is randomization for primality testing. So how do we find out if something is prime? So any suggestions based on our previous lecture? And that was numerical algorithms. Anyone remember? What would you do? You know how to find if a number is prime. What would you do? So you can see if 2 divides it evenly. You can see if 3 divides it evenly. You don't usually do 4 because you already checked 2. You check 5. You don't check 6 because 6 is a multiple of 2 and 3. So you don't check things again. So you have what's called the sieve of Eratosthenes, and use those numbers and you check if they divide evenly. And you cross out any multiples that you've already tested so you don't have to test them again. We said you could stop that check at the square root because no factor is going to be bigger than square root unless it has a cofactor that you already got. So this is a randomized algorithm, and it makes use of something called Fermat's little theorem, because Fermat's little theorem says that if I take a number a to a prime p modulo prime, I'm going to get back the a that I started with. All right. Anyone know why I call this a little theorem? Is because it takes a little bit of space. Anyone know why it's called a little theorem? What's Fermat's big theorem? So Fermat's big theorem is actually not called Fermat's big theorem. It has another name. Anyone know what it's called? Should have learned this in 120. Anybody? So I remember when this was a theorem that was around for centuries and it was unproven. And back, I think it was 1994, I think I was a grad student and teaching at City College. And a guy by the name of Andre Weil, from originally British, and then he was at Princeton. I think he proved it using some elliptical equations stuff, which is pretty remarkable because that's not specifically integer related. Okay. And it was used to do things in integer number theory. So that's a pretty cool proof. Okay, so that's Fermat's last theorem. This is big theorem. This is his little theorem. Okay, so the question is, this is true for a prime number. Okay, it's proven that this is true for a prime number. What happens if p is not prime? Anyone know? So the answer is it is rarely true. It can be true, but it's unlikely. Okay, so you see this thing here? It says that if C is composite, meaning not prime, it's possible but unlikely, and we call them pseudo-primes or Carmichael numbers. Okay, so there are a bunch of them, and it's like big news when they discover a new one. Okay, they get pretty big, these numbers. Okay, so how are we using this as for randomization? So here's what we do. We say we're going to try this for a bunch of different A's. Okay, we're going to try this for a bunch of different A's. So if you look down in the slide where we're trying it for 10, we're trying it for 17, we're trying it for 21, and we see, does it work? Is it true that for a given number P, that a to the p is equal to a modulo p, right? So we're looking, okay, is 10 to the 96 mod 97, is it equal to 1, right? So you can either do it with a to the p or a to the p minus 1, compare it to 1. So that's what we're doing. So if it's true for all the different values of a that we try, then we are going to conclude that it's prime. Now, is it necessarily prime? No, it's not necessarily prime. It may not be prime, but it's unlikely that it's prime. So it's sort of like the Bloom filter, right? It says, listen, for this to work, by chance, for 10 different values of a, unlikely. So we're going to come to the conclusion, which may be a faulty conclusion, but a likely conclusion that P is prime. So that's a randomized algorithm. Okay, so this is one of my favorites. Okay, I actually did this in a database course. So we wrote a stored procedure and some built-in functions to actually do this with the database. But you don't need a database to do it. That's just because it was a database course. So here's what we do, right? We know that pi r squared is the area of a circle. You also know that if I have a radius of 2, or a diameter, meaning a width, which is also a height, right? So that's the area of, and I square that, so that's the area of a square. Okay, so you know what? Okay, so the question is, what percent of a circle inside a square is the circle inside the square, right? So here's what we're going to do. Oh, there it is. Everyone see that? So there's your unit circle. Everyone see that? So what would happen if we made a square around the circle? And I started to throw darts and see how many times, okay, and the darts were guaranteed to get into the square, but they weren't guaranteed to get into the circle. So I say, what is the probability that it's in the circle? And that depends on pi. Okay, so why don't we, let's do an experiment here. Okay, so here's what we're gonna do. I'm gonna go to, do I have this? All right. All right, so remember this spreadsheet? Where do we do this? Is this the fractions? Square root. Okay, so here's what we're going to do. Okay, so we're going to call this okay, so we're going to make, here's my x, and here's my y, and my x is going to be a random number. Why doesn't it like that? How do I get a random number in, anyone know how to get a random number? Ran between okay, I'll use ran between. So we're going to say rand between, we want to get a number between -1 and 1. Didn't like that either, because I can't spell. I can't type, actually. I can spell pretty well. I'm bad at typing. Okay, and we also want decimal places. That's important here. Why is that? How do I get a decimal number? Anyone know? Let's try this. R-A-N-D. Okay, let's try that. Okay, but I want a random number between 0 and 1 and -1 and 1, so I can do this. Okay, and I need to do that over here. Okay, good. Okay. So there's my X, my Y. Just align it better. Okay, so the next thing is I need to determine if it's in the circle or not. So how do I do that? Well, I take A squared. So I say A2, and I square that. That work? No, how do I square it? How? Do it times itself. Plus B2 times B2. And I take the square root of that. Okay, so the origin. Okay, and then so we say in circle, okay, is if C2 less than 1, I get a 1, otherwise I get a 0. Let's see if that works. Okay. All right. So here's a approximation. And then what I do here is I count. I say count of, well, you know what, I can do a sum. So D2, D21. Okay, so that means 15 of my 20 points are inside the circle. And then over here, I need to figure out pi based on that. Okay, so let's go back to the slide. So the slide said that pi is equal 4 times the number of points divided by the number of points in the square. Okay, so pi is equal to 4 times D1 divided by 20. So that's my estimate of pi. Now that's not a very good estimate of pi, but what we can do here, go up to, so what I found with my database class is we needed to go to like, thousands. Okay, see if we can get a better estimate this way. So now instead of 17, we need to go to D101. And over here, I need to divide instead of by 20, I say 100. That's a little bit of a better estimate there, okay? All right, so we can use a randomization, random points, essentially like throwing a dart at a dartboard to calculate or estimate pi. So by the way, is that a Monte Carlo algorithm or a Las Vegas algorithm?
Monte Carlo?
That is Monte Carlo. Why is it a Monte Carlo?
It doesn't loop forever and it's going to approximate.
Okay, so the time it takes is fixed, right? If I have 100 points, it's always going to take 100, the number of points that I use. But the accuracy of it, right? I'm never going to get exactly pi. And as we saw, it could vary considerably, right? So obviously the bigger the n, the better the accuracy, but there's no guarantee. All right. Another option is, another example is what we call load balancing. What is load balancing? Load balancing is where we have to assign tasks to resources. Okay, this comes up in networking, for example, right? You have too much work, so you offset it onto another computer or operating systems. So how do you figure out who should get what? Well, one thing you could do is you take turns. So every time I get a job, I assign it to the next person, right? So you go A, B, C, D, then back to A. But maybe A had some big jobs, so A isn't finished yet, and D had a small job or is very quick and is sitting around not doing anything. So round robin isn't such a good approach, right? Another thing you could do is, well, look at, what their load level is, right? You figure out how much work do they have left, but then you have to figure out the min each time. So that's also not good. The random, you randomly assign jobs to different things, and therefore you don't have to really ask any questions. You don't have to make any judgments. And on average, things are going to sort of work out. All right. So that's a strategy you can use. You can also use it to generate strong passwords. Okay. So basically what you do is you take the password that the person wants to use, and then you randomly generate some characters at the end or in the middle or at the beginning, just to make it a little bit stronger, right? Random walks, talked about this before. If you want to go in a particular direction, we're not going to do it in this class, but that's sort of a fun assignment. I don't know if you've ever coded a random walk, but you get some really cool patterns that emerge. Random colors, right? So if I want to have a random pixel, I assign it a red, which is a number between 0 and 255, the number between 0 and 255 for green, and a number between 0 and 255 for blue. And I put those together using the RGB function, and now I have a random color. And you can get some cool patterns that way that look something like what we saw over, there. Okay. It does make for a confusing background. Okay, so we can do that. All right, so here's one last problem. Then we're going to do a little coding exercise together. Right, let's say I want to determine if a particular matrix is the product of two other matrices. How do I do that? Well, the first thing is the dimensions need to match. Okay, so that means that the number of rows in A and the number of columns in B needs to be the same as the number of rows in C and the number of columns in C. So if those aren't true, it's just wrong. The other thing is, in order to multiply A times B, the number of columns in A and the number of rows in B need to be the same. So you need to check all those things. Okay, so that's sort of the pre-work. But then we could use brute force. Okay, how do we use brute force? Well, how many elements are in matrix C? So you take the number of rows in C, which I call RC, and you take the number of columns in C, which I call CC for columns of C, and you multiply them. That's the number of elements. So for each element, I can check, is it the dot product of that row with that column and B? And if it matches, it matches. So how much work is involved? How much work is involved? Well, for every element in C, I have to compute O of n. So if we assume that these are all n by n matrices, so I have to do n times O of n squared to verify each cell, and that is equal to O of n cubed, right? Or I could just do the matrix product from scratch using Strawson, and it takes me n to the log 2 of 7, which is around n to the 2.8. Okay, so that's not really good, but I could use a randomized approach. Okay, so the randomized approach is called Freivold's algorithm, and it says, listen, don't check every element. Pick a few elements and see if it equals to the dot product. Now, the likelihood that it matches, any given one, let's assume that it's 50%. In reality, it's less likely than 50%, right? Because it's just a number. So the probability that I get the right number just like that is very small. But even if we assume it's a 50-50 chance, right, that a particular number is going to match, and I try that for k different numbers, instead of all n squared, I tried for k different ones. So probably if they're all going to work is 1/2 to the k. That's a very small number. Or the probability that it'll match when it's not correct is just 1/2 to the k. Okay, so that is another example of a randomized algorithm. And again, this is a technique. Now, obviously, the strategy is to figure out, when the randomization is going to help, right? So there are really two pieces to that, which is, how much does it reduce the time complexity? And also, how likely is it that you're going to get the right number? So if you're, likelihood you get a right number, like in Bogosor, is 1 out of n factorial, that's not a very good use of a randomized algorithm. Okay, so what we're going to do now is we're going to code assignment number 8 together. And as we start the assignment, I'll explain to you why this is useful. But first, I need a volunteer. So this may be the last opportunity. Oh, we have 2 people who raised hands. Okay. So Ming, did you go already?
No, I haven't.
No. So Ming, why don't you go? So I'm going to enable the screen sharing. And again, make sure to share your whole screen. Close any tabs you don't want everyone else to see. And this is a cool assignment for a number of reasons. So as Ming is getting ready to share PyCharm and to share the assignment and to have a Google ready if we need to look up anything. So let me explain why we want to do this assignment. So number one, the first thing we're going to do is we're going to run a way you would do a recurrence equation, the way you would learn, let's say, in an intro course. And you're going to find that for n not so big, it is already impossible. Okay, it's not practical. So that's why you're going to need step 2, because step 2 is going to show you a better way to do it in general, a generic code for occurrence relations. So that's another thing. And it's a technique that we talked about in a different context called dynamic programming. It's called memoization. So the idea of memoization is to preserve the recursive flavor of an algorithm, but also to remember old results. So I create a little bit of an infrastructure for remembering results. But first, I want you to do step 1. So create a new assignment 8. Okay, you can get rid of any code, except for the basic stuff there. You could leave the imports in case you need them, but all that stuff you can get rid of. Just keep those last 2 lines on the bottom. Okay. Yeah, you can get rid, just get rid of most of the main. We don't need that. Good. Okay, great. All right, so let's copy that traditional Fibonacci. So this is the way you would code Fibonacci numbers, if you're learning about recursion in your intro to programming course in Java or C++ or Python, it doesn't really matter. It'll all look roughly the same. And we're going to call that traditional Fibonacci with 10 and print out the results. Okay, so from your main program, call print Fibonacci, traditional Fibonacci, and try it with 10, and that'll probably run quickly enough. Okay, it is 55. Okay, fine. Now try it with 100. Is it running? Ming, is it running?
Yes, it's running.
It's running. Okay, notice it's taking some time. That's not so surprising, because remember what the time complexity is. It's exponential. So maybe 1.5, 1.6 to the 10 isn't so bad, but 1.6 to the 100 is pretty bad. So I'm going to ask you to kill it. I think we've convinced you already that's not a very good way to do it. So you can leave that code there, but the purpose of that was to show you why that's a bad approach. All right, so what I want you to do now is copy those lines from section 2, task 2. And what we're doing is we're building a dictionary of dictionaries like we did in some of the other algorithms, but here we're not keeping track of time actually. What we're doing is we're keeping track of the values. Okay, so each dictionary represents a different function, and within each dictionary, we keep track of that function for different values. Okay, so what we're going to do now is, I told you to do one for merge sort, so I guess just to follow the assignment, let's follow the instructions. So copy that code. And in another step, I ask you to make a comment. So I don't remember where I put it, but okay, so make a comment there before that. Actually, better yet, just change the name of the function. So instead of def F1, say def F1 merge sort. Okay, so each function will be the complexity of a algorithm, or we'll know what it is. And fine, we'll say if n equals 1, we return 0, the number of comparisons for merge sort. Otherwise, we call our helper function, okay, and we multiply it by 2, just like in merge sort. So if you want, just do this. Put a comment before that line, before the function. No, before the function. So we understand what it is. So do t of n equals, so just so you understand what this is really saying. T of n equals 2 times t of n divided by 2 plus n. Okay, so you remember that? Okay, so now what we're going to do is we're going to, and let's go to line 4, section 4, and create that function there also. So the call and print you're going to do for the main. So just get those 2 lines there. Okay, great. And now, now take that call and print, that 1 line there, the call and print, and call that from your main. Okay, and you can get rid, you can delete or comment out the print traditional Fibonacci because we know that that's too slow. Okay, so let me tell you what this is doing here, right? We're going to call our F1 with an n equals 256. Why 256? Because that's a nice power of 2, right? It's a nice power of 2 to the 8th. And we're passing in a string so we know what to print as a description. Okay, and run that. Okay, so it finds the value of it. Now, what we're also going to do, if you copy the code from line 5, okay, paste that in, and we're going to give that a name. So we'll call that print dicts, print dict or print dicts or something. Give that a name. We're going to define a function, main. Def space print dict, or dicts, D-I-C-T-S. Good, and just indent all that code. Okay, good, and I think that's great. And now if you could call that from your main. And run it. Okay, what happened there? Where's the error? Click on the link. What's the problem? the func is a function. Okay, can you print func in the line right before we do func.name, because it's complete. No, you can't do it there. Over there, exactly. Print func, because I don't know, somehow func is not what we think it is. So that's the name. Anyone see the problem? Click on the error. Okay, do this. Print dict funcs. Before that, before the loop. Okay, so we're getting merge sort. You know what it is? Maybe it already is the name. So get rid of line 57. And get rid of line 57 again. Okay, and just change, you could say, instead of func name, just say func. And change it there also. Maybe it already is the name. Okay, run it again. Okay, look at that. So look in the console. Look in the console, and it's saying with input of 1, we get 0. With an input of 2, we get 2. With an input of 4, we get 8. With an input of 8, we get 24. With an input of 256, we get 2048. All right. So we have this nice little helper function that allows us to study different recurrences. Okay, so this is a cool program in and of itself. So for our next function, I want to do Fibonacci again. But this time we're going to do it using our helper function. So we're going to define F2, and it's best if you put F2 right after F1. So they'll always be in order, so we can always find everything. And we're going to call this Fibonacci. Fibonacci. And we're going to always have the same parameters, func and n. And we're going to say, how did you get all that in there already? How did you get all that code there? Did you copy it from the other one?
Oh, it's a plugin in PyCharm. I can turn it off.
Wow, that's so cool. Okay, great. So let's make sure it uses eval func. That's good. Wow, it's so smart. That is great. Okay, so here's what I want you to do just before that. Let's put a little comment right before the function. Put a comment. Yeah, right there. And just say f of n equals f of n, well, not n, f of n equals, I like that plugin, equals f of n minus 1, f of n minus 1. Now, f of n minus 1. Like that. There you go. Is that the plugin again doing all that work for you? All right. Does a plugin do the exam for you? No?
No.
No. Okay. So now what I want you to do is call that one. So go down to, now remember, 100 didn't work before. Do Control D on line 73. Change that to 2 Fibonacci. Yeah. Use the same 256 and just change the the caption. So in line 74, change it to what it really is. Okay, good. Wait, what did you do there? Hold on, what did you do there? Fix that, please. No F event, there you go. Okay. Look at that. Okay, it finished in no time whatsoever. Everyone see that? So if we did it the traditional way, 100 didn't work. We waited, right? Now we did 256 in no time at all. Okay, let's scroll to the right so you see actually how big 256 is. And go all the way, real far. Numbers get nice and big. You see that? Okay, but our program isn't scared of that. All right, so think of this as a review opportunity. So I want us to, and everyone feel free to chime in. Okay, so I'm going to bring up the chat here on my end and think of examples from recurrences from the class. Okay, anyone have any suggestions, or you want me? Okay, here's a advanced one. Okay, we're going to do F3. And we're going to do parallel merge sort. Parallel, we're going to, instead of parallel merge sort, we'll call it improved parallel merge sort. Good, okay. And we're gonna, so I don't remember what the initial conditions are. You could just say if n equals 1, n equals 1, return 1. Turn 1. Okay, where's the else? Okay, remember this? So we're going to do eval function func int of 3 n divided by 4. Okay, plus outside of that, no, outside of that, outside the eval func, plus int log of n divided by 2. Remember that? So where did this number come from? We can't say 3n divided by 4. You have to say 3 times n. Sorry, you can't do that in Python, right? You need a time sign. Okay, and it doesn't like the log. Does it like the log? It's hard to see. You know what, Ming? If you can go to full size here. So we don't need the assignment anymore. Just go to full size. Take up the whole screen. There you go. All right. Is it underscored? I can't tell. Doesn't know. Try math.log. It likes that. Okay, do you have to import math? Why doesn't it like math? Does it know what math is? Oh, it's good now, right? It was slow? Okay, fine. All right, so remember what happened. We have 4 subproblems, right? We have the 2 halves of the top, 2 halves of the bottom, but one of them is going to be very small, right? And then we need a log of n to do the binary search on one of them, but each one is half the size. Okay, so let's call that. You want to change the caption? Yeah, that looks good. That looks good. Okay. And we have What's it complaining about? Oh, because you need to return. You always need to return eval func. Okay, run it again. Okay, notice it goes up very slowly, right? In the slides, we showed that it was log n times log n times log n, very small number. Okay, so here's what I want to do. I want to go through slides or our memories to find other algorithms. Let's do bubble sort. Okay, so you can make a bubble sort. Okay, who remembers the recurrence for bubble sort? It's not just for bubble sort, but anybody? Okay, so if n equals 0, if n equals 1 rather, return 0, right? Why? Because there are no comparisons. Else return eval func func n minus 1 plus n minus 1. So it's not one comparison, it's n minus 1 swaps in each loop. So instead of that 1, it's n minus 1. Plus n minus 1. Okay, can you write the recurrence in normal English on top of the as a comment? So over there, we want to comment? What comment should you have? Plus n minus 1, right? Okay, let's, do we call that? Okay, so while Ming is working, coding away, can people suggest recurrence equations from the class that we can build into this? So otherwise you get to do the rest of it on your own. So the more that Ming codes on our behalf, the further along everyone is in this assignment. So you can go to slides, pretty much every lecture it's some kind of recurrence equation, but not necessarily.
Recursive quicksort?
Well, I want you to write the recurrence equation in the chat. So go to your slides, notes, SciBook, internet, wherever, and find recurrence equations from our course. And then we'll modify them to turn them into Python. But if you can get us the starting point. Okay, so that was bubble sort. The numbers look, they look reasonable. Yeah, that looks good. Okay, so while we're waiting for suggestions, can we do linear search? So copy the bubble sort. So if n equals 1, return 1 because it's one comparison. Otherwise, eval function of n minus 1 plus 1 operation in linear search. Okay, good. Update your main. Change the comments, description rather. Good. Okay, is that for quicksort? N minus 2, how do we get n minus 2 for? Right, so selection sort is too similar to bubble, so I'm not going to do the one for selection. We did linear, that's good. Okay, now copy linear and let's do binary. Binary search. Okay, and you're gonna do, if n equals 1, you'll do 1. All right. So you need to eval function for n divided by 2, right? Line 95 is going to be int of n divided by 2. And 1, actually it's plus 2 operations, right? Because we really need to check left and right. That one's going to be f of n divided by 2. Okay, good. You run that. Okay, great. You see how it's much smaller then? So it had 256.17. Go to linear search for 256. Linear search 256. Go to the right, all the way to the right. It's the last number. Going, one more. There you go. Is that right? How's linear search? Or is that a different one? All right, that looks better. Yeah, that looks right. Okay, I've got some other ones for us. How about long integer multiplication? Long integer, we'll call it DNC. Long integer mult, or just integer mult. Integer mult. And okay, if instead of DC, you could say DC, divide and conquer. Okay, so if n equals 1, it's going to be 1. Otherwise, it's 4 times eval function. Oh, you need to write a comment before binary search. Good. Okay, so DC integer mult, so it's 4 times eval function. It's half, each problem is half the size plus, let's say, n. Now, in theory, it's really O of n, but we can't solve recurrence with O of n here. So instead of 2, it's n. Okay, and then put a comment for the function. Okay, we need we're going to need more examples here. So that's good. Okay, call that from your Ming, can you make your font a little bigger? Is that possible? Ooh, okay, good. All right. Okay. All right, so now we're gonna do Karatsuba, integer mode Karatsuba. Just copy all that, great. And you want to have 2 blank lines between functions. So if you have more than that, you can get rid of some of them. Yeah. Karatsuba. It's with a K. Karat, A-T-S-U-B-A. Integer mode. All right, good. So it's going to be 3 times n over 2. 3 times f of n. And the rest you could leave the same. So now we're going to find out, does it really help? And it does. Look at that. See that? Okay, let's do matrix mode, DC matrix mode. Good, so we have, remember, 8 subproblems. Each is half the size plus n squared. Okay, it's really more than probably some multiple, but we don't know what that multiple is, so we're going to ignore it. All right, in line 112, you could change that. Okay. If you know what the coefficients are, feel free to add them. Okay, good. All right, now we're going to do Strawson matrix mode. What changes for Strawson? Who remembers?
7 subproblem.
7, correct, 7. Somehow we lost 8. So do Control D on one of those, yeah. What was 8? There we go.
Just 3 times.
Okay. So there is a difference between the Strawson and the other one, right? You see those differences. Okay. Next up, I think what else we have? Here's what we could do. We could look at old exams. So go to the Google Drive. And in the old exams, so let's go to the one, let's go to the midterm. The midterm is the one with a recurrence. You could go to either the solutions or the regular. So grab that recurrence there. Yeah, if you want to create the function first. So we'll call it F11 midterm, winter 2022. And copy in that recurrence. Good. So, and the base case is n equals 1. That's good. So 125 times eval func of int of n divided by 5 plus 5 times n. Okay. Now, in this particular case, we have a result on the bottom, right? So we can compare it. Okay, instead of passing in 256, so let's go to the bottom. Let's go to the, let's use multiple of n. So let's do 120, let's do 625. Okay. Okay, great. Let's run that. And what did it tell us? It tells us the values. Go to the bottom of these solutions and see what value it came up with. So it was T of 5, right? T of 5 is 150. Is that what it says there? You see that? 150. Okay, that's lovely. Okay, good. Let's do the midterm from spring to summer 2021. And then I almost found one in an older exam. But let's do the one. Let's do that one there. That was summer 2021. Okay, so first of all, the base case is T of 1 equals 2. N equals 1, return 2. Good. And in the main case, we're going to do 4 times int of n divided by 3 plus n. Good. And call that one. And let's pass in a power of 3. So let's do 243. 81 times 243, yeah. Okay, look at the answer and let's see that it matches up. So T of 3 is 11, T of 3 is 11. That's nice. Okay, Oma found us one in an older exam. So this is very similar to the divide and conquer, but that's okay. So we can call that midterm spring 2016. Let's change that sprint to spring. Okay, only you want to find us some other ones while he's coding there? Did you do 2n? Did you change it to 2n? Ming, I didn't catch. Did you change it to 2n there? Yeah, good, good. Okay, Elma, you have anything else for us? How about someone else? Pretty much every semester should have one or more recurrences. By the way, it doesn't have to be. Okay, Ming, why don't you do this? Why don't you open up the old exam PDF? That one. And let's go through it and look what there is. There are different kinds of recurrences also. So there's some with characteristic equations. We didn't really spend a lot of time on those in this course, but maybe we have, okay. Yeah, so that's, you could do that one. You could do that one. So Meg, Elmo gave us one in the chat. You see anyone with a characteristic equation? Those are a little bit of a different flavor. One that looks more like, say one that looks more like a, okay, I've got a good one for us in a moment. Now, of course, we wanted to, we could graph these, right? And then you get to see, you know, the different curves. Oh, by the way, for the one with the n divided by 2, so I would go back to the 256 for those, by the way. So number 13 and 14, 13 and 14, switch back to 256. Okay, I've got a good one for us. Okay, I want you to Google Catalan numbers. Catalan, C-A-T-A-L-A-N numbers. Okay, click on that Wikipedia article and we should see a recurrence for it. Okay, so I'm not interested in that. You see a recurrence equation? Scroll down. Okay, there's a recurrence equation right there. You see that right where your mouse is? So let's create F-16, like the fighter jet, F-16. Okay, and we're going to call this Catalan numbers. All right, so this one's a little bit more involved. Okay, so our base case is C of 0. So if n equals 0, return 1. Now we need a sum. Okay, so create a variable called S, I guess, for sum, or C. How about C for Catalan number? C equals 0. Make a loop. You could say for I in range n. Okay, C plus equals eval function, and it's hard to see what it says there. What is it? C of I? Point your mouse to the recursive formula, please, on the left. What does that say? Move to the left. No, go to the left, a little more. Don't jump back and forth. Go to the left, go to the Wikipedia article. A little more, right? Yeah, that one. Okay. Okay, beautiful. Okay, so we have, no, so we need to go to n minus, that's good. C of I. So in the eval function, you're going to pass in func, comma, I. Func, comma, I times eval func and minus I. Okay, I think that's good, but we'll find out if it is because we know what the numbers ought to be. And then you're going to return C. Okay. By the way, I'm just thinking, yeah, that's good. That's good. Okay. You're going to call that and see if we get the right numbers. These numbers get very big, by the way. I wouldn't even go to 2, just do 100. It's, we're getting maximum recursion depth exceeded. Okay, we shouldn't get that because we're doing this the right way. Let's go back to your code again. Why? I thought the beauty of this is we don't care about recursion depth. Okay, hold on 1 second, please. I apologize.
What if C is equal to 1?
Okay, let's run that with the smaller number and make sure we're getting the right answer at least. So do they have some examples? Go to the Wikipedia on the left-hand side. And do they have some values there that we can check for getting the right answer at least? Okay, so just go to Google and say list of Catalan numbers. Oh, there are some. Okay. So let's do 10 for starters and see if we get those. Okay, so something is off here. Okay, go back to the function. Okay, stop. Aha. Okay, I think I know what the problem is. So we need to look at this formula, and we're not computing n plus 1, we're computing n. So that means we need to go up to n minus 1, which is what we're doing in the range. And then we should have, that's our problem. So we have C of I is good, but this should be n minus 1. So change that to n minus 1 minus I. There you go. Now run it. Okay, are we getting the right numbers? So go 1, 1, 2, 5, 14, 42, 132, 429, 1430, 4862, 16796. Okay, now let's go to 100. So change that to 100. We just had a bug. There we go. Look at that. Okay, if you try to compute this the regular way, it's not going to happen. It's not going to happen. Okay. Here's what, let's Google this. Let's Google famous recursive formula. Famous recursive formula. So Fibonacci we did. Okay, let's find another one. Something else. I got one. No. Oh, yeah, here's a good one. How about sum of squares? Called sum of squares. Okay, so if n equals 0, n equals 1 rather, it'll just be 1. Else, it'll be return. So it'll be the eval func of n minus 1 plus n times n. Yeah. Right? So that's a sum of squares. Okay. That's a famous sequence. Like 1 squared plus 2 squared plus 3 squared. You could, whatever, you could leave it 100, that's fine. Okay. That's good. Okay, now let's go back to the sum of the squares. How are we doing on time, by the way? Oh, you know, class is over, I'm sorry. All right, so everyone gets to do 3 more. So here's one that you should do, sum of cubes. And 2 more, okay? All right, so you can find 2 more. All right, we should have some in the slides. You don't need a plot. You don't need a plot for this. No. Oh, Lucas numbers, that's another one. Lucas numbers is like Fibonacci, but no, it's not. It's just different base case, and we have, what's that next one after Lucas? That looks interesting. Whole numbers, what does it say? Hell? You do that. Okay, all right, great job, Ming. Thank you for being our class coder today. And sorry, I went overboard. Okay. All right, take care, everyone. Bye-bye.